Hello, in this video we're going to look at the joint probability distribution. Joint probability distribution actually is two-dimensional probability. The function fxy is a joint probability distribution or probability mass function of the discrete random variable if fxy, we know that probability should always be bigger than 0 or equal to 0. The second one is you take the summation of all x and all y, all the probability together. If you add all of them together, then equals 1. And number 3, you have probability of x equals small x and the y equals small y equals fxy. Okay, this is the three basic properties or definitions of the joint probability distribution. Okay, you can look at the example 3 yourself. It's not really hard, you just add everything together. Basically, it depends on what you calculate. Okay, for example, let me see. Two ballpoint pens are selected at random for a box that contains 3 blue pens, 2 red pens, and 3 green pens. If x is the number of blue pens selected and y is the number of red pens selected, so find the joint probability of fxy. Then the joint probability distribution is you select x from 3 because you have 3 blue pens. So the fxy equals, you select 3, x from 3 is, x is the blue pen, so choose x from 3, and choose y from 2, y is the number of red pens. Okay, then you have 2 minus x minus y, and choose from 3. What's the meaning of that 2 minus? You have the joint probability distribution. The first one is x is the number of, this is blue, this is red, and also you have green. Okay, so that's if you draw two pens, like you only draw 2, right? So x plus y, this is blue and red and green. So blue plus red plus green together equals 2. So this is for blue, this is red, then the green is going to be 2 minus x and minus y. And also the total probability is going to be just to choose 2 random from 8. That's the probability distribution. Then you have a table. You let x equals 0, x equals 1, y equals 0, y equals 1, x equals 1, y equals 0. Basically, you're going to have the table 3.1. You have x equals 0, y equals 0, and x equals 0 have 3 things. Y equals 1, y equals 2. Like you put all of them together and you form a table. So x 0, 0, y x 1, 0. So you have x equals 1, you also have y equals 0, y equals 1. Okay. So basically, because you only draw two balls, you can only have y equals 1. You can't have y equals 2 because together it has to be 2. So basically, you find you have x equals 2, and then y has to be 0. Okay. So you have all the probabilities, and you find that, and it's going to be a table here. Then the next is the joint density function. So joint density function is for continuous random variable. The continuous random variable, you have also the probability is always positive, bigger than or equal to 0. Second one, if it's continuous, you can take the antiderivative take the integration from negative infinity to positive infinity, fxy dy equals dx dy, because two-dimensional and equals y. And 3 is you find the probability of xy. Okay, in the sample space A is, well, it depends on what space you want. Okay, for example, sometimes people say, okay, x is less than 1, bigger than 1, less than 2. So you just put the boundaries 1 to 2 like that. Okay, just like a calculus problem. So you have 3.15. I believe is not really hard. It's just antiderivative. You find the boundary is normal antiderivative things. Okay, so I really think that if you take calculus 1, calculus 2, this should be okay, easy things for you, okay? Just first one, you check if it's equals 1. If it's equals 1, yeah, it's a proper distribution. Second one, from 0 to 1/2, from 1/2 to 1/4, you put them as the two double integral. Find the antiderivative for x and find the antiderivative for y. It's really simple. Okay, if you need help, I can give you some help on the antiderivatives or integration. But let me know, please. And the marginal distribution is that for the x alone and the y alone. If for x alone, you have to take all the y together. Okay, for the y alone, the marginal distribution, you have to put all the x together. For that, you have to take the antiderivative for x. Okay, I think you can look at the examples yourself, and let me see. I want to look at the conditional distribution. Conditional distribution, you have f, y given x. So here you have to use the probability of x, y both happen. Okay, and then also you have the denominator is what? It's x. So you have to find the marginal probability distribution of gx, okay, and the gx is marginal distribution, okay. So gx is going to be defined as take the negative infinity to positive infinity fxy, and you say fxy dy, okay, and fx, so dy, this is the gx, okay. So all the y together is marginal function of x. So this is the conditional probability. And you have the other one, x depending on y, so the denominator changing to y. Let me look at one example, see. Okay. Look at 3.19. The joint density function for random variable xy, where x is unit temperature change y, is and y is proportion of a spectrum shift that a certain atomic particle produces fxy. So fxy equals 10xy squared, 0 less than x less than y, and 0x elsewhere. Find the marginal density function for gx_h1 and the conditional probability of fyx. So first, find the marginal function. Marginal function is the fx, and take the antiderivative from negative infinity and fxy dy, right? However, because this only have 0 to x to y, it's going to be the is 0 to x to y is this function, elsewhere is 0. So the boundary at anywhere else, if it's not between 0 to 1, is 0. So it's going to be just a 0 plus, and it's from for gx is from, because y is bigger than x, x less than 1, so it's x to 1. Okay, then fx dx is 10xy squared and dy. Now we take the antiderivative with respect to y, so it's going to be 10xy cubed over 3. Plug x into 1. Plug 1 into here, so it's going to be 10 over 3. Plug x into here, so it's going to be 3 10x cubed. Okay, that's going to be your density function. That's going to be, sorry, marginal function for gx. In the similar way, you can do the y as well. Okay, so I'll skip the hy. Is the same idea, but you have to just pay attention to the boundaries of y. Okay, then the conditional probability. If you find fy over x, fyx, and then this is going to be the probability of x and y over the marginal function of f of gx. And now fxy is given as 10xy squared, and gx we just find is 10 over 3, and there's an x, you plug 10, there's an x here. Okay, so you have x minus 10 over 3x cubed. Okay, then you multiply everything by 3, and you can cancel the x out, then 10 is cancelled out, 3 is going to the top, is 3y squared. 3 goes to the top, 10 cancelled out, and x cancel out. You have 3y squared over 1 minus x cubed. Plug this x times another x, it's called power 4. Is x cubed. And 0 less than x less than y. So this is the conditional probability. Okay? And I think this independent. In the previous chapter, we have introduced the independence. If the probability fxy equals gx times hy. So, which means that the conditional probability does not actually change, does not affect it. And if the x1 and y be two random variables, discrete or continuous, if they have fxy, the joint probability distribution equals the product of the two marginal distribution is going to be independent if this happens. Okay, if this happens, is independent. So you just need to check that. Okay, so you can read more examples. I'll provide another video for you to help you with your homework. Okay.